and welcome back or welcome to my channel. In today's video, we will be going over some of the applications of Newton's laws and how we can use Newton's laws to solve complex dynamic problems. A lot of these problems are common dynamics problems that you will see in your problem sets, quizzes, or even AP exams if you guys are interested in taking those AP exams. So let us get right into one of the first types of problems that you will see a lot, which are problems that involve pulleys. So in this case, we have a block on a table and one block hanging, and both of them are connected by a cord that wraps over a frictionless pulley. So block S over here, we're going to set the mass as 3.3 kilograms. And then block H over here with the smaller m, we're going to set that to 2.1 kilograms. Okay, and then we're going to say that the cord and pulley have negligible masses compared to the block, so we don't have to care about how this motion affects the cord and the pulley. This just simplifies the problem a little bit and makes it easier for us to focus on the blocks. Okay, so the hanging block, or block H, falls as the sliding block S accelerates to the right. So A, we're going to find the acceleration of block S, and B, we're going to find the acceleration of block H, and C, we're going to find the tension in the cord. Okay. So let us start by drawing some free body diagrams. So I think we went over free body diagrams briefly in the last video. And free body diagrams are basically just simplified ways of visualizing and representing the forces on a body. So it can make it easier to see the components of the forces, the components of the net force, which will in turn make it easier to apply Newton's second law. So starting with block S, let us think about the forces that are acting on this block. So in all cases, there will be a force of gravity on the block acting at the center of mass. So this is the force of gravity on block S. And then similarly, there is going to be a normal force from the table. And this normal force is equal in magnitude but opposite in direction to the force of gravity because block S is not accelerating in the y direction. And then the cord here pulls and applies a tension force to the right. So we're going to add a tension force to the right. So those are the three forces acting on block S. And I should also specify that the surface of the table is frictionless, so there is no friction acting on block S. If you want to make this problem a little bit harder, you can go ahead and add a force of friction in there and see how that changes. But for this one, we're just going to ignore friction. Okay, moving on to block H, we similarly have a force of gravity pointing downwards, but with a smaller magnitude than that on block S. And then it's not on a table. There's no other perpendicular force acting to it. So there's no normal force. And that counteracts gravity. Instead, we just have the tension force over here that points up due to the cord. And here we should notice that block H is going to be accelerating downward. So this is the acceleration downwards. So we're going to make sure that the force of gravity on block H is greater than the tension on block H. Okay, so let's get to actually solving the problem. So let's represent block S, the big block on the table, as a particle of mass m. So here is block S, and here are all the forces that are acting on it. Okay, so these are all the forces that are acting on block S. And then on block H, the hanging block, here are all the forces acting on block H. And notice how I draw these forces so their magnitudes are relative to each other. because T over here should be less than the force of gravity on block H, so the arrow is thus shorter. But the normal force here is equal to the force of gravity on block S, so the arrows are of equal magnitude or size. Okay, so now that we have the free body diagrams, we can apply F net equals ma to the sliding block. So for block S, or the sliding block, we have in the x direction, F net in the x direction is equal to m times the acceleration in the x direction, and the net force in the y direction is equal to mass times the acceleration in the y direction. However, F net in the y direction is 0 because we have Fn equals Fg on S. So this just tells us that this becomes 0. So there is no F net in the y direction. So ultimately this tells us that only in the x direction is Newton's law important in our case. And we can do the same for block S. Sorry, block H. I keep on confusing the two blocks, block H. So we can do the same for block H. So we're going to apply F net in the y direction because that is the only block H force that is important to us. So we have F net in the y direction equals the mass times the acceleration in the y direction. Okay. Now for these two equations, we can substitute the forces in them. So for block S, we have the only force acting in the x direction is the tension force, and that equals the m times acceleration in the x direction. And for block H, the forces acting in the y direction are the tension force and the force of gravity on block H, and that is equal to the mass times the acceleration in the y direction. Okay, and now we can substitute for the forces of gravity, just mg, and we get this simplification. And note that these two equations are simultaneous equations with the same two unknowns, tension and acceleration. And because these two blocks are connected together, their accelerations will be the same. So here we can simplify this and say that this just becomes m times a, and this also becomes little m times a. So now all we're left with is trying to find t and a in both of these equations. And we have two equations and two unknowns, so this can easily be solved. So subtracting these equations will eliminate t, and then solving for a, we get that a equals m over m plus m times the force, the acceleration of gravity. And then we can substitute this into the equation t equals ma to get that t equals m times m. Sorry, there should be a big M. M times m, g over m plus m. And putting in the numbers, we get that the acceleration is equal to 3.8 meters per second squared, and the tension equals 13 newtons. Okay, so this is one of the first types of problems you will see. So moving on to the next type of problem, we're going to look at a cord that accelerates a box up a ramp. Okay, so as always, we're going to have to reproduce this problem visually. So let's just say we have a simplified ramp over here with a box on it and a cord pulling it upwards. Okay, So a lot of people consider problems involving ramps or inclined planes to be especially hard because your frame of reference is rotated. And we have to work instead of a full gravitational force with the components of the gravitational force. So in this example, this is a pretty typical example. And in the tilt, the key idea is to apply Newton's second law to the axis along which the motion occurs. So in this figure, a cord pulls a box along a frictionless plane. So let's just specify that there's no friction at an angle of theta equals 30 degrees. And the box has a mass m equals 5 kilograms. And the force from the cord has a magnitude T equals 25 newtons. And the question asks, what is the box's acceleration along the inclined plane? Okay, so the acceleration along the plane is set by the force components along the plane, not by the force components perpendicular to the plane or anywhere else. So we need to write Newton's second law for the motion along the appropriate axis. And because the box moves along the inclined plane, we should rotate our normal axis. So this is our normal axis, right? So we have the x and the y. But since the box is on the inclined plane, it would make sense to rotate our reference axis into something like this, where the x-axis just matches parallel to the direction of the box's motion. And this will make it a lot easier to solve the problems. So now that we have chosen a coordinate system, we can draw a free body diagram with a dot representing the box. And then we're going to draw the force vectors on it. Okay, so looking at this picture over here, we have the normal force from the inclined plane that points in the positive y direction here. This is the normal force. And then we have the force of gravity pointing downwards as always. And then we have the tension force from the cord pointing along the positive x-axis. Okay. Now, after we have done this, we can start by looking at the angles and how this can help us break up certain forces into their components. Okay, so the gravitational force Fg is downward and has a magnitude mg, which in this case is equal to 49 newtons. Okay. However, the force of gravity is split into two components in this case. There is a force of gravity in the x direction and a force of gravity in the y direction. Okay, so we need to find an expression for the component of the force of gravity in the x-axis. Okay, so we're going to start with a given angle of the plane and work our way to a triangle of the force components. So here is a simplified representation of the plane again. So we have theta over here, and then this is our force of gravity pointing downwards, okay? And this means that this angle over here, we know that this is 90 degrees minus theta, because this is a right triangle. And we already have 90 degrees here, and we know that a right triangle has to add up to 180 degrees. Okay. So one component of the force of gravity will be parallel along the plane. So we can draw the components of the force of gravity like so. There's going to be two components to the force of gravity that will form their own right triangle. So this one over here will be the force of gravity in the x direction. And this one over here will be the force of gravity in the y direction. So just by doing this, we have broken down the components. And here again, this will be theta. And what that tells us is that the force of gravity in the x direction is simply mg times sine of theta. If you know how to do trigonometry, some simple trigonometry, you'll know that this component, the x component, will be mg sine theta, and the y component is mg cos theta. And now we have the components of the force of gravity. And we have one more force to consider, which is the normal force. However, it is perpendicular to the plane, so this can't affect the motion along the plane, since it has no component along the plane to accelerate the box. Okay, now that we've dealt with all the forces, we can write Newton's second law for motion along the tilted x-axis. And we get that the net force in the x direction is equal to the mass times the acceleration in the x direction. And the component ax is the only component of the acceleration, since the box is not like jumping up from the plane or descending into the plane. So we can simply write a for the acceleration along the plane to make it a little bit simpler. And because the tension force is in the positive x direction and the component mg sine theta is in the negative x direction, we can write this as t minus mg sine of theta. And substituting the data and solving for the acceleration, we can rearrange this to say that a is equal to t minus mg sine theta over the mass. And you can plug in all the values, and this will give you 0.1 meters per second squared. And this value is a positive value, which indicates that the box will accelerate up the inclined plane in the positive direction of the tilted x-axis. Okay, so let's move on to the next type of problem here, which will deal with a force within an elevator cap, which is honestly one of the most difficult problems that a lot of students face. And it is a very common problem, so you will definitely meet this sort of problem. Okay, so let's just say that we have an elevator over here, and there is a person standing within the elevator. And there is a scale that the person is standing on. Okay, and this person has a mass of 72.2 kilograms. Okay, so we're concerned with the scale readings when the cap is stationary and when it is moving up or down. So we're asked to find a general solution for the scale reading, regardless of the vertical motion of the cap. The reading is equal to the magnitude of the normal force on the passenger from the scale. And the only other force that acts on the passenger is the gravitational force. So we can draw a free body diagram with a dot representing the person. And then here, the force of gravity points down, and the normal force from the scale points up. And the normal force is what the reading of the scale will actually be. And we can relate the forces on the passenger to his or her acceleration, A, by using Newton's second law. However, we should remember that we can only use this law in an inertial frame. And if the cap is accelerating, then it is not an inertial frame. So we're going to choose the ground to be our inertial frame and make all measurements of the passenger's acceleration relative to the ground. So because there are two forces on the passenger and their acceleration are all directed vertically along the y-axis, we can use Newton's second law for the y components. And here we get that the normal force minus the force of gravity is equal to the mass of the passenger times their acceleration. And we can rearrange to get that the normal force is equal to the force of gravity plus the mass times the acceleration, because we're interested in the normal force or the reading on the scale. And this tells us that the scale reading, which is equal to the normal force, depends on the vertical acceleration, and we can substitute mg for the force of gravity to get mg plus ma and simplify using the distributive property to get m times g plus a for any acceleration a. For example, if the acceleration is upward, a would be positive, and negative if it was downward. So we can go ahead and work on this problem with a few more specific values. Let us imagine that the elevator is stationary or moving upward at a constant 0.5 meters per second. In both cases, the acceleration is equal to 0 because it is either stationary or the velocity is some constant value. So the acceleration is equal to 0, and plugging that into the equation that we get that the normal force is equal to the mass times g plus 0 for the acceleration. So it's really equal to the force of gravity on the passenger, and this is 708 newtons based on the values that we have. So now, what if the elevator is accelerating upward at 3.2 meters per second squared? And what if it's accelerating downward at 3.2 meters per second squared? For the first case, when it is accelerating upward, we have the normal force equals the mass times g plus 3.2 meters per second squared. And plugging in the values that we have, we get 939 newtons. In the second case, when the acceleration is downward, we have the same values, but this time the acceleration is a negative value, and we get 477 newtons. All right, for the last question, during the upward acceleration over here, so when it is upward accelerating at 3.2 meters per second squared, what is the magnitude F net on the passenger, and what is the magnitude of the acceleration as measured in the frame of the cab? So the magnitude of the gravitational force on the passenger doesn't depend on the motion of the passenger or the cab. So we know that the force of gravity on the passenger is still 708 newtons. Okay, and the magnitude of the normal force from the elevator on the passenger during the upward acceleration is 939 newtons during the upward acceleration on the scale. So the net force on the passenger is simply equal to the normal force minus the force of gravity, as we stated at the beginning over here. And that is simply 231 newtons. And this is during the upward acceleration. However, in the frame of the elevator, the passenger's acceleration, let's just call it A passenger relative to the cab or the elevator, is equal to 0 because they're accelerating at the same rate. So in the non-inertial frame, the net force on the passenger is not equal to m times the acceleration of the passenger relative to the cab. And Newton's second law does not hold, which again tells us that Newton's second law only holds for inertial frames. Okay, so thank you very much for watching. I know this video was a bit longer, but it was important to show some of the applications of Newton's laws and how we can use them to solve various types of problems. These are really common problems that you'll probably see a lot throughout, like practice problems wherever you look, and even AP exams. So I hope this video helped you guys a little bit in understanding the very basics of applying Newton's laws and working with the problems, and I hope to see you guys in the next video where we will be going over more specifics of forces and their applications in motion.